Hello class, it's Mr. Hofstede. This is our wrap-up of simple harmonic motion, the second video. A lot of this is review, and some of it is outside of the curriculum, like damping for the most part. So just let's get through this nice and quick, and if you have any questions, feel free to let me know. So damping is kind of in the curriculum. It can help your understanding of oscillations in simple harmonic motion, but it's kind of an extra little bit of information. So this isn't essential, and you won't be directly tested on this, but here is some fun extra knowledge about damping. So as we saw with the masses in the lab video I posted, all the spring masses will eventually slow down and reach this equilibrium position. Well, they'll stop oscillating, and that has to do with the friction in the spring. We don't have an ideal spring. Same thing for a pendulum. Eventually the air resistance will slow down an oscillating pendulum until it's no longer moving. So damping is that decreasing of the amplitude until it eventually reaches zero. So everything in the real world will eventually slow down and be damped and eventually reach this rest position. So there's different types of damping. This first one, under damping, is when it takes a longer amount of time for it to eventually come to rest than our next two situations. So this is more similar to what we saw in the lab, where the mass did oscillate and eventually slowed down. There's not a ton of damping here compared to some of our other ones, but it takes several oscillations before it finally comes to rest. Overdamped won't even complete one oscillation, right? It'll slowly, what this would look like, if you can see my cursor here, is if we're thinking about the mass on the spring, like the last question, it would slowly come down and stop without coming back up at all. So you can kind of think about this like an airbag or something, right? Where there's not a full oscillation at all, and it takes a long time for it to reach that rest or equilibrium position. So it takes a long time, but it's reaching that equilibrium without actually completing one full oscillation or going through one period. Critical damping, this is a fun one. If you go into engineering, there's a whole physics course on simple harmonic motion, and there's a portion of that course that's focused on damping, and critical damping is an important concept in that. And critical damping is when we reach equilibrium in the shortest amount of time as possible. So you can see that we're coming to this equilibrium position a lot faster than we did with our overdamped, right? If we have time on this x-axis and our displacement on the y. So the shortest amount of time it takes to reach equilibrium without having passed it and come back up and completed a period would be our critical damping. So that's it for the kind of extra material on damping. Here's a nice visual for them all. So overdamped takes a really long time, doesn't even go past its equilibrium position, comes to rest in the same place. And the underdamped is kind of more of a real world situation where it'll eventually reach the rest position, but it takes a long time, and it's doing several oscillations up and down, full periods. All right, resonance. This is review from Physics 20. We'll go over it pretty quickly. So every object has a natural frequency where the atoms within it are happiest vibrating at. So every tuning fork that you hit will have a different pitch because the metal atoms within it are vibrating at that favored or that most common frequency. And when we are applying an external force, whether that's by pushing a swing that's in phase with or in line with the natural frequency. So we need to have the same frequency as our natural frequency when we're pushing it or when we're applying external force. Then we'll get resonance. And there's some cool videos if you want to check it out, right? The classic breaking a wine glass, just using your voice. If you're an awesome opera singer, you can match the natural frequency of the wine glass with your vocal cords. Then, right, eventually everything will continue to shake and amplify. So that's a big part about resonance. You're increasing the amplitude through constructive interference. Here's another cool one, a tree they made in Britain that's using the wind and resonance in these tubes to make a bigger noise. For now, we're going to not do this practical. We'll see how things turn out with this whole situation. But I know I gave you this handout. We're not going to do it. We're going to just move on to electrostatic or electric circuits next without doing this practical. All right, our 4.2 PowerPoint. A lot of this is review. We get a little bit into some new things like electromagnetic radiation, which is a physics 30 concept, but pretty much all of this is covered in the Alberta curriculum. It's just presented in a different way, and I'll highlight kind of the extra stuff that you should be aware of. So we know that a traveling wave is something that transfers energy without all the particles within it actually moving or experiencing any net motion. So they can still move, but they won't, they'll kind of return back to their starting position. So if you think of, video isn't working, but if you think of this as one particle, as the wave propagates, whether it's longitudinal or transverse, it will always come back to the same position. All right, and this is true for any particle. So we're not having a shift of the actual particle or through a shifting in the matter. Instead, they're vibrating and sending this energy to the particles beside them, right? And we get this kind of chain reaction domino effect within the particles that are right next to each other that transmits energy over some distance. So wave fronts are, each of these circles would be a different wave front. This is kind of a new way to look at a wave front. It's the part of the wave that's in phase with the particles around it. So here we have some central source that's propagating waves outwards. So each of these waves, each of these particles on this wavefront would be in the same phase at the same time, whether that's at a peak or a trough. And rays will indicate the direction. We talked about this even more extensively in Physics 20 than it does here. They need to be at 90 degrees to the wavefront, and they show the direction that the energy is actually transferred through the wave. All right, so transverse again is up and down, as you can see in this little animation, and the direction would be perpendicular to the particle's motion. So we did this with their giant slinky, right? When we moved it up and down, we saw the wave fronts travel and the energy transfer as a result perpendicular to the oscillations. Here's some fun animations. This is a personal favorite. Classic transverse wave GIF or GIF. Don't want to offend anybody. Just quick terminology review. We got the peaks, we got the troughs, and these are where we're seeing transverse waves most often. Water ripples, light or electromagnetic radiation, which is a physics 30 concept, is also a transverse wave. We saw it with the rope or the slinky, like they're showing here. We did that in class. And we got earthquakes. There's different types of earthquakes. They can actually be longitudinal. This is an S wave earthquake. Did some fun geology courses on earthquakes and the different types of waves they can emit. So that's just a fun geology nerd add-in. All right, so whereas transverse had to have the oscillations perpendicular. Now longitudinal, the oscillations are parallel to the direction of the energy transfer. So these are kind of like compression waves, we like to think of them. And you have to have a source oscillating still, just like a transverse, but now it's pushing the particles forward, right, as wave fronts, and the oscillation is parallel to the direction of energy transfer. So we call them zones of compression when they're closed in together, right, the compressed particles, and zones of rarefaction. And if you do look at our GIF up here and you kind of trace one particle, it's just vibrating or oscillating back and forth. There's no net movement of these particles, just a transfer of energy. Longitudinal waves, we have sound waves. We focused in a lot on that. You can also get it on a slinky when you do kind of that compression motion of it, and our P wave earthquakes. Water, we got circular wave. It's doing both transverse and longitudinal motions at the same time, and it looks like it's traveling in a circle, so we call it circular wave. All right, displacement is the distance from our equilibrium position. We're all familiar with this. I'm going to go through it really quick. Amplitude is the displacement at a peak or a trough, the maximum displacement. Period is the time taken to complete one full oscillation. And frequency is how many oscillations we get per second, and it's measured in hertz. Wavelength is the distance between points that are in phase. So often we'll just look at two peaks, how far away they are, or the same point. It doesn't matter what point you choose to measure from, just make sure you're starting and ending at the same point. So here, we would start at this point, go through a full oscillation, and end back at the same point. And these points are always in phase, so they move together in step. Wave speed is how fast the wave fronts will pass by somebody observing, right? How fast they're actually moving in the direction that energy is being transferred. And our super important formula here, frequency is 1 over period, or period is 1 over frequency. That's because period is measured in seconds, frequency is hertz, or 1 over second. So just by looking at their units, we can come to that formula. And the wave equation, we got the speed of the wave is equal to its wavelength divided by period, where wavelength is measured in meters, period in seconds, so we get meters per second. So derive this again using units, and you should have no problem with that. Try doing these questions on your own. It's good review, but I'm not going to go through it with you. There's all the answers. Try to do it without the answers. You should have a worksheet. Let me know if I didn't attach it with some practice for these waves. Not much new if you don't do the worksheet because you're feeling comfortable with this and confident that Physics 20 prepared you good enough. Fine. If you do want extra practice, here this is for you. All right, this is new information. This wasn't covered in Physics 20, and it is pretty cool, pretty important stuff. So if you fell asleep, time to wake up and pay attention to this stuff. So we're very familiar with looking at displacement time graphs. Be careful whenever you're looking at these wave graphs, you're identifying what each of the axes are. That's important for any type of graph you're working with. So displacement time graph, right? Y-axis is displacement, x is time. We are always looking at the movement of one point of the wave over a period of time. So this is, if we pick one of these particles in our GIF right here, we're just going to follow along that one particle, and it's going to trace this displacement over time. Right? It's not giving us a picture of the whole wave, just of one individual point or one individual particle. We can get the period from this, right? Because period is the time to complete one full oscillation. So using a displacement time graph, an important piece of information, you can draw out of it is the period, right? Because it's measured in time, just like period. And this is an important note, this can be representing either longitudinal or transverse, right? Doesn't matter what particle we're looking at. So for longitudinal, you just have to use left as positive. So sorry, right of the equilibrium position as positive and left as negative, right? Whereas with this one, we would have up as positive and down or below the equilibrium as negative. Okay, but these can represent either transverse or longitudinal. All right, this is new to us. We haven't come across these distance displacement graphs before. Again, pay attention to our axes. We have centimeters and centimeters. So this is new. This is, right, a weird type of graph, not using time, but using the distance. So what this is able to tell us is a more holistic view of the entire wave, but it's just at one moment in time. So it's like you took a picture of the slinky going through its motion at that time, and you can determine what each part or each point on the slinky, how far away it is from equilibrium, right, at any distance from either of the ends. So distance displacement graph will give you an instant snapshot or a picture of the entire motion, but just at one moment in time. And since we're working with centimeters here, we can actually find the wavelengths. Whereas before with distance displacement or distance displacement time graph, we could find period because we're looking at seconds on our x-axis. We're working with centimeters on our x-axis in a displacement distance graph, which will give us the wavelength. So again, we can either have transverse or longitudinal. All right, electromagnetic wave or electromagnetic radiation. This is physics 30, so you will go quite in depth on this in physics 30. I won't stress you out, make you learn it all right now, but look forward to more of this in physics 30. So electromagnetic radiation is a type of transverse wave. We can see, right, we have the up and down. We also have a horizontal wave. So what's really happening here is we have an electric field and a magnetic field running perpendicular to each other. And they're transferring energy from some oscillating charge, usually an electron. So we have some important things you aren't really required to memorize as in depth with the Alberta curriculum. You do need to know these numbers for Alberta even. I think we usually round that to 400. But in the IB, there's more wavelengths, more frequencies to have memorized. So our visible spectrum, Roy G. Biv, goes with wavelengths of that electromagnetic wave ranging from 700 to 420, which means that, right, the spacing between two of our electric field peaks or two of our magnetic field peaks is between 700 and 420 nanometers, right, where nano is times 10 to the negative 9. So ultraviolet is like superviolet, so we're going to place this in our spectrum outside of the violet. It's even more violet, that's how I like to think of it, than our violet. So we're working with wavelengths from 10 to the negative 7 to 10 to the negative 9. So we're getting shorter wavelengths, right? And when we have a shorter wavelength, that means we have a higher frequency. So these are smaller wavelengths progressively. So X-rays are past our ultraviolet, which as we're going right, we're progressively getting smaller and smaller wavelengths, higher and higher frequencies. So an X-ray will have a wavelength from 10 to the negative 9 to 10 to the negative 11. So in Alberta curriculum, we really only need to know the range of visible light and then the order of the electromagnetic radiation spectrum, right? So if you know that ultraviolet comes after visible and then X-ray comes after ultraviolet, that would be enough. But for the IB, you need to pay attention to our orders of magnitude and the range here. All right, so X-ray, you do need to memorize for your IB papers, occurs from 10 to the negative 9 to 10 to the negative 11 meter wavelengths. And our smallest wavelength is our gamma rays. And here we have 10 to the negative 12 to 10 to the negative 15. All right, so those are all of our shorter wavelength electromagnetic radiation waves. Then our visible spectrum. Now we're going the other way. We're going to the larger wavelengths. So if we have ultraviolet being like superviolet outside of violet, now we have infrared, which is even more red. So we're going past the red side of the visible spectrum. And this is a bigger wavelength now. And this is what we think of as heat, right? Our infrared cameras are our heat detecting cameras. And even bigger wavelengths than infrared would be our microwave, going the wrong way there, which is 10 to the negative 2 or 1 centimeter to 10 to the negative 3, 1 millimeter, right? So the wavelength of a microwave is between a millimeter and a centimeter. And then we have radio waves, which have the biggest range of all, and you can go up to a kilometer. So some of those will be on the scale of a mountain even. So you do need to know the order as well as the order of magnitudes of each of their wavelengths. Don't worry about memorizing the frequencies as well as the wavelengths. Choose one. The wavelengths are nice and simple here. And then you can convert wavelength to frequency using the speed of light, which is given on your data sheet, and our wave formula, where speed is equal to our wavelength divided by our period, or wavelength times frequency. So this is all physics 30 stuff. I won't spend too much time on it. Right, light can travel in a vacuum. We already alluded to that in physics 20. And in a vacuum, it'll always travel at the speed of light, 3 times 10 to the 8 meters per second. They're transverse waves and they're electromagnetic waves, where we have the electric field and the magnetic field perpendicular to each other. So this is kind of what you need to know for the IB. And there's a video put out by NASA that I attached on the assignment. That's a good run over of that. Sound waves we spend a lot of time on. We have oscillations parallel because it's a longitudinal wave. So you're compressing the particles in the air and they're moving out as these sound waves, with compression and rarefaction zones. So you hear sound waves because they're going to vibrate to your eardrum, right, and send signals to your brain that is interpreted as sound. Amplitude is about energy, and when we're talking about sound, it's also about our volume, right, because sound waves that have larger amplitudes, right, would have more energy, and we're going to perceive that as louder noises. And pitch is all to do about frequency, so how many of these we get per second. So shorter period, higher frequency, higher pitch. And just fun little bio throw in. Humans can hear frequencies of all the way up to 20,000 hertz, right? And that'll change over your lifetime. You're all young. As long as you don't listen to too much loud music in your headphones, you're going to have a better range of hearing than your parents, than me, and especially than your grandparents, because we're going to lose that over time. So measuring the speed of sound, we're just going to use distance over time. If you take the average of 3 times, it's going to be a lot better. You can try to do this in your own homes even, using some software, right? If you have a mic like that, or you could come up with different ways using your cell phones, I'm sure. We're not going to do any of that though. That's more covered in Physics 20. So in a solid, sound can travel at approximately 6,000 meters per second. In liquid, it's 15, so it's slowing down as we're getting less dense. And in air, which is what we're used to curing things in, we're traveling at approximately 330 meters per second. Often you'll see that rounded in Alberta to 300 meters per second. This is a little more exact though. Right, so as we're getting denser, our particles are closer together, so we're going to be able to transmit oscillations between those particles faster, right? And as they're spaced out more, there's more time for this water molecule to hit the molecule next to it because there's more space between them. So it's going to slow down the speed of that longitudinal wave. And the least dense, the most time between particle collisions is air or gas, is going to be the slowest propagation of that. Sound in a vacuum does not exist, and that is a good meme. Echo is just a reflection of sound, so whenever you're working with something bouncing off something coming back, remember we're working with 2 times the distance. Easy to underthink these, oversimplify them. Just remember that it has to go there and back, so sound isn't traveling 50 meters, it's traveling 100 meters. All right, 2 down, 1 to go. We're going pretty good. There's a lot of review in here. Hopefully it's a nice, easy lesson for everybody. I did not watch this GIF yet. It's a goodie. It's probably a weird Guinness Book of World Record for human dominoes on beds, and I love it. All right, there's more new information on this slide. Again, if you have any questions, feel free to ask me and I can see if I can clear it up for you, or maybe make another video, or give you direction to another video on YouTube or wherever that can clear it up for you even more. So wavefronts are the parts of the wave that are traveling together, side by side, in phase, just like the ripples in a pond. Okay, here's our new stuff. Intensity. Wave intensity is defined as the amount of energy per time flowing through an area. So we already know that energy per time is power, or we should know that. And we measure power in watts. So if we have energy per time, or watt, flowing through some area, right, we're going to have units of power per area. So it's watts per meter squared. All right, so intensity, easiest to think about it as light. This is kind of our most common intensity type question. An example would be if we have a window with an area of 1 meter. So try to imagine how long a meter stick is, right? And now we take 2 of those, put them at 90-degree angles. That would encompass 1 meter squared. If 1 joule of light energy flows through that window every second, right? So 1 joule per second would be equal to a watt. So 1 joule per second through that 1 meter squared window, we would say the light has an intensity of 1 watt per meter squared. But it makes sense that as you get further away from a light source, it's going to appear less intense. And I did attach another video that breaks down this formula. This is actually the intensity of a point source that would send out its energy as a sphere. So from the center of whatever it is, whether it's a speaker or the sun, it's going to be emitting its energy out in all directions equally, right? As long as it's kind of thought of as a single point that's emitting its energy. So if we have energy leaving our point source in all directions, it's like it has a sphere around it, right? And we need to find the area of that sphere that we're actually interested in, that we're measuring, whether that's the Earth relative to the sun, or whether that's your window relative to the sun. But as we get further away from that source, we're going to be having a larger and larger area of that sphere that is encompassed by where we're at. So that video should have some good visualizations for that for you. So that's where we're getting this 4 pi d squared, right? So d is thought of like the radius, and 4 pi r squared is equal to the area of a sphere. And as we get further away from our source, from a light source, we're getting a larger and larger area of the sphere that's being covered. So the intensity is equal to P, the power of the light, so that would be in watts, divided by the area, right, using the spherical area formula. So the further we get away, we're going to get much smaller intensity, right? So we have an inverse squared proportionality between intensity and our distance. Here's a good graphic, right? So if you extend these squares, these pieces of fabric, all the way around our sun or this original light source, right, we would form a sphere. And when we're nice and close to it, right, our area is nice and small. As we get further away, you're going to have a larger area that needs to be covered by the same amount of energy from that light source, right? So if we're increasing area, which is on our denominator in our intensity formula, but keeping the same amount of energy from that light source, we're going to be decreasing the intensity, right? Hold P constant, that's our energy or our power, energy per second. And we're increasing the area on the denominator, we're going to be decreasing the intensity, right? Just think about it as a light bulb in the center of a dark room. When you're nice and close to it, it's really bright. As you move away, we're going to be getting a lot darker really fast. It's growing at this exponential, or it's decreasing at this exponential rate. So you are given this idea that the intensity is proportional to the inverse square of x, where x is the distance from our light source. All right, there is another YouTube video talking about the connection between intensity and amplitude of waves. And it explains that when you look at the area under the sine function, as you increase the amplitude, the area under it increases exponentially, right? And intensity is all about the area covered by the power. So if we're increasing the increasing the amplitude, the intensity will increase exponentially. So increasing the amplitude or the energy of the wave, right? So if we doubled our amplitude, we're actually going to quadruple our intensity. So we have exponential growth in intensity as relative to our increase in amplitude. So the proportionality here is the intensity of the wave is the square of its amplitude. And we do have this k as some constant. So it depends on what we're looking at with the wave, what that constant would be. But we'll always have intensity being proportional to the square of its amplitude. Right? So if we double the amplitude, the intensity quadruples. Surfers are aware of this. You get a really big wave, its intensity is so much bigger than you even could imagine. Another worksheet. This one I recommend doing because it's new material. So, superposition. We did this in physics 20. I didn't show you a stellar GIF like this. I should alternate between GIF and GIF. I'll try my best. But we have constructive versus destructive. So this green wave is our first wave. This blue wave is the wave it's interfering with, and that black wave is the resulting wave. So when our first two waves are on top of each other, right, we have fully constructive interference happening right now. And then once they are exactly out of phase with each other, they're fully destructive, right? When their period is 90 degrees off, pi over 2. So superposition, when we have two or more waves meeting, the resultant displacement is the sum of the individual displacements. And we did lots of fun worksheets with this. I know Jaden really loved this part of Physics 20, especially drawing stuff like this. Right, there's another good GIF. GIF, it was GIF's turn. So these are our two waves that are coming into contact with each other. Here's our interference pattern. So when they're exactly out of phase with each other, we get zero superposition or zero resultant wave. So you add them to produce a resultant wave, right? And we can have negative or positive. So be nice and sure that you're keeping your positives and negatives straight. And if you want a nice rabbit hole on this type of material, check out Fourier series. I don't know. I think Bonin was doing that for his math or something. But Smarter Every Day, Desmond does a really cool episode on Fourier series and combining sine waves in different sequences, and he can pretty much draw whatever. I don't remember if I showed you guys that one, but that was an awesome one. Worth another watch. Yeah, this is pretty overwhelming when you're doing it by hand. Good thing we have computers that can create our resultant waves for us, but who knows, maybe on your IB paper they'll make you sketch this by hand. I have never seen that, but be an interesting curveball. Alright, polarized waves is briefly covered in Physics 30. It's just taking transverse waves, running them through a filter, and then polarizing the waves, essentially. So when our vibrations are in the same plane as the filter, they'll go straight through. When we have this 90-degree difference between the plane that our filter is on and our vibrations plane, we'll get fully destructive interference, right? So we have no constructive interference here. All we can get is destructive, and it's essentially filtering out the wavelengths that are perpendicular to the filter. So light from the sun usually comes unpolarized, right? So it's traveling in all directions. When you're looking at it head on, you'd see light poking out at all directions. From the side, it might look something more like this. If we run it through a filter, right, either one of those, actually this one looks like it's going through a vertical filter, then we're going to get this resulting polarized light where we're eliminating all of the horizontal, all of the light that's not in the same plane as our filter, right? And we'll get our resulting electromagnetic radiation or light looking like that. Fun background information. This was how they came up with these Polaroid cameras. So unpolarized light going through a polarizer. And we're getting exactly 50% through this one vertical filter or polarizer. So super important to remember that we get 50% of light going through a polarizer. If we just do a vertical, right, our resulting light will be vertically polarized. If we do horizontal, we'll have horizontally polarized. It's just getting rid of all of the light that's in a different plane than the filter. And if we have horizontal and vertical, almost nothing will come through. Theoretically, nothing should come through, but sometimes you'll get a little bit that sneaks its way through. And this is all outside of both the IB and Alberta. So read it if you're interested in Brewster's angle. This was in a university course of mine. I don't even remember which one, but we're not going to spend time on it unless you're feeling like you want some extra learning. A lot of this is related to physics 30 stuff, our incident angles and our optical densities. That's all covered in physics 30, so I recommend you wait until then. I believe one of the students did their IA on this last year. So if you're really interested in light and polarization, that's an option. Optical activity related to optical density, which is covered in physics 30, and it's just how easily light can travel through something, right? So something like glass would have a low optical density, whereas something like syrup, something like that, the light will travel slower through. It'll be more optically dense, have a higher optical density value. So optically active stuff will change depending on how much of the molecules of the solution are present and what angle you're looking at. And a classic example of that would be a sugar water. Another fun side note. You could try out those worksheets. A lot of this requires some prior knowledge from physics 30, but as far as polarizing lights go, you should be able to figure out some of that just from these PowerPoints, from my little talk through it. If you want to do this worksheet, it would be good for your learning, so you can go ahead and do that as well. All right, we did it. That was quick. See you guys next week. Good luck with all the homework.